Hi, my name is John McCullough, and this is my 103 midterm number 2 explanation video. We start off by just drawing out the figure again and deciding what our control volume is going to be. So at the end of the day, what we want is we want the tissue and then a little bit of just the tubes and everything that's coming out. So we have the leak, of course the tube that goes to the right where the mass leaves, and the tube to the left where the mass enters. Right here we have our assumptions. And what we start off doing is we start off by looking at the cone and finding out that we will need to know what the radius is, just in case later. So we can do a little bit of geometry, and we can get the radius in terms of height. And so we have an equation for the radius, for the total radius, as basically in terms of time, which is going to be important because the water will decrease in level and the radius will change. So actually the first thing we do is, because we want to find out how much the mass of the liquid increases inside the tissue, we need to know how much mass enters and how much mass leaves. So we can start off by looking at this right side where the mass leaves the pipe and then fills up a cup. So what we know is that the mass that leaves this tube will equal the mass that enters this cup, and the mass that enters this cup will be the change in volume over time times rho. So what we can do is we can actually use what we know to figure out the mass flow rate. So what we do is the volume in the cup is shown right here. It's just the height in terms of time times the area, well, the cross-sectional area, of course. And so we can of course plug in what we know, and we can figure out the mass that enters the cup, which would be this. Later on, even though this isn't really necessary per se, I still found out the velocity of the mass that leaves this tube. It's not really necessary because we already know how much mass leaves the tube, and that's all we really need. We don't really need the velocity. So then later on what we do is we focus on the cone, because we need to know how much enters from the cone, how much water enters. So we can do the same thing as before, where we changed the change in volume over the change in time times rho will give us the mass flow rate. So we can start off doing is we start off by doing we know the volume of a cone, but in this case it's the volume of a frotum, is the bigger cone minus the smaller cone. So we need to do a little bit of geometry. Then we know everything, even though it's a little ugly, but we have all our values. And right here, all I'm doing is I'm starting with the mass flow rate that enters is equal to dv dt times rho. And so we're just plugging in the volume that we know. Of course, we have to multiply it out because some of these terms are additive and we are taking derivatives. So all of this right here is just writing everything out for the volume, taking a time derivative because the height of the water, so the height of the cone, is decreasing with respect to time. We multiply by rho to get our mass flow rate, and then we simplify because a lot of terms cancel out or add up. Then once we have the mass that enters from the cone, we have the mass that leaves from the tube, and of course the mass that leaks depends on this first mass flow rate. We have everything we need. We just need to do the conservation of mass because mass doesn't get destroyed. So d at the big derivative, capital D of m of t is 0. So we know that m in minus m out minus what gets stored inside of the tissue, which is dm dt, which is what we're solving for. So of course we set dm dt equal to m1 minus m2 minus m3, but we know m1 and m3 have a special relationship. So we can just plug in this equation times 0.99 because 1% of it leaks, which means not all of it will be entering in. And then of course we have the m2, how much leaves through this pipe. And so we get a nice equation. Well, it's not exactly very nice. We get this equation. So for number 2, what we do is similar to number 1. We set up a control volume, which will be the water entering here, the water splattering out, and of course this this cart moving to the right. And this force right here will be pointing to the left because the water will be pushing it to the right and accelerating it to the right. So right here we just have some of our normal values, just everything written out, the assumptions. Of course, this is just to show why all of this, all the water splashing out is irrelevant. This is just the explanation right here. Of course, just showing that the force in the y and the force in the z will be 0 because there is only really the jet pointing to the right that is going to be accelerating much. So, for part A, we can focus pretty much just on the x direction because that's how the brakes are applied. We know that the density is constant throughout. We know it's negative fx because it's pointing in the left direction. And so we have this right here. We have this equation, and we could solve this, but to simplify it, we know that it's a steady control volume, not deformable. So we can use the linear momentum equation for a traveling control volume. We ignored this, right? This section of the code, the equation. And instead of v, we have w, which is the relative speed, which is v1 minus the control volume. So it's the liquid entering minus the control volume. And we know that is 25. And of course, we have to make sure all of our notation is correct, like w times n. So it's moving to the right, but the normal force is pointing left, so it's negative. And so we simplify it down to this equation because w and rho are uniform throughout the control volume area. And so of course we just plug in our values and we get 357 newtons, but of course it's pointing to the left. So it's 357 newtons to the left. For part B is quite similar, except now we have to account for the water jet going up and to the right, which will cause some forces in the x and some forces in the y. So we have the same assumptions. We're going to use conservation of mass to figure out that, of course, m1 must equal m2, so the water entering the control volume must be the water leaving, or the mass flow rate. So we could do, once again, conservation of momentum in the x direction, similar to the last problem, but of course we have to take into account that there will be a W1 and a W2. So there will be water in the x direction, like this, and then there will be another one, like that. And they will actually have opposite effects because right in here, we can see that the normal force and the velocity are in opposite directions, so W1 will be negative, right? But W2 will not be negative because it's in the same direction as N2, and that makes sense because if the water was getting forced back, it would be W would be multiplied by 2 because you would need extra force to push it back. But in this case, we're just diverting it, so we're not holding all of the water back. We're just kind of letting some of it go through, kind of. That was a bad explanation. But we know that the N2 and W2 are in the same direction, so we just take the component of the x, which is cosine of 45. So we do the same thing. We know it's W times rho times the sum of the w's times n. And of course, we know that, once again, f of x is negative. We go back here and we can solve f of x, which is the force of the brake. The brakes are applied in the x direction. But right here, all I did was I also found it in the y direction. Of course, going back to here, in the x direction, we understand that, never mind. Okay, that's it. Yeah, that's it.